Okay, so hi everyone. Welcome to the Grothendieck School of Thoughts. This is the sixth lecture of our motive series and the second lecture on Nori Motives by Professor Kapil.
Yeah, so today I've tried to do it with slides so that things are a little better. Okay. So, how do we get the classical homology functors? That is by taking a functor from the category of motives to the category of abelian groups, which sends hn, little hn xy to capital Hn xy, that these are the usual singular homology groups. So that's the basic idea. So in order to do this construction, we want to introduce something which I talked about last time. So I just want to run over it again. So, which is to talk about diagrams and R-linear abelian categories. So given a category C, we have a directed graph whose vertices are the objects of C and edges are morphisms in C. And for a directed graph, a map of diagrams is just a map of directed graphs from the graph to the underlying graph of C. Maybe just touch this. That works. Okay. For a Noetherian ring, we let mod R denote the category of finitely generated R module. So note, this is important. It's going to be finitely generated, and the fact that R is Noetherian is going to be important. I mentioned this last time. And an abelian category is said to be R linear if the group of morphisms between objects is a finitely generated left R module, right? And composition gives you a bilinear map, R bilinear map. Okay, so that's what we say, R linear abelian category. In general, we would like something more about R linear categories, which we'll come to maybe at a later point. Okay, so the main construction of Nori is the following. Given a diagram, I have a segment from G, here it's B. So I have not edited the file very well. Okay. Given a diagram G and a commutative Noetherian ring R and a map of diagrams from G to R modules. So as I mentioned last time, in most of our applications, R will be one of the following. It will either be integers or rational numbers or some field, some characteristic 0, some field. Okay, so some, maybe that's all. No, maybe you need QL. Or maybe the underlying field for the varieties which we are looking at. So it could be QL. It could be QL or it could be the underlying field. So we'll see why that comes up at a later stage. Okay, so the idea is that you should be able to factor. So you've already got a diagram. I mean, think of the situation of varieties. You already have a diagram of varieties. So we'll mention what exactly that diagram consists of later. And you have a functor, which is the usual singular homology functor. I want to factor it through motives. Okay, so the motives will be this guy, and this factoring should be universal. This factorization is universal in the following sense. That given any R linear abelian category with an R linear faithful exact functor, so again this is G. this is in some sense, the idea is that this A, this is the smallest, within quotes, of course. Okay. So it's the smallest in the sense that whenever there is a factoring like this through an abelian, R linear abelian category, it produces a functor S tilde from this to this. So this will be used because for ordinary cohomology theories, we have, for varieties, we have many cohomology theories. Okay, so the examples will be the examples for S in our case is going to be things like, of course, singular cohomology itself is there, which is P itself, but you could also take, for example, what is called algebraic de Rham cohomology. Okay, you could take L-adic cohomology. Okay, and you could, or if you are very fancy, you could take crystalline cohomology also. Now, you might wonder, why do I need this at all? The reason is that as it stands, the singular cohomology functor will depend on a choice. So, of course, we are going to work with varieties over a field K, and we are going to choose an embedding of K in C. Okay. And using this embedding of K in C, so this choice will give rise to singular cohomology, because it's actually for the topological space associated with this particular embedding of K and C, okay, Q coefficients or Z coefficients. If I change the embedding, it is not immediately obvious that I get the same groups. In fact, there is a classical, of course, for homology it is actually isomorphic, but in fact, there is an example due to Sayre, which shows that you can take the same variety, and for different embeddings of K and C, the fundamental groups are not isomorphic. Okay. So you start with a variety and take an automorphism. So what can happen is that here I can take an automorphism of C, and this will give me a different group, H and sigma of X, C, Y, C, Q, okay, for the different embedding, sigma. And it's not clear how to make an isomorphism between these two. Of course, in the case of homology, these groups are actually isomorphic in the sense that they are of the same dimension. But there is no isomorphism naturally associated with sigma that we have. Okay. So there is a problem. So one way to resolve this problem is to use L-adic cohomology, okay, or algebraic de Rham cohomology, both of which are defined without any choice of embedding, and thereby prove that whatever construction we have is independent of the embedding. Okay, so though the construction depends on the embedding, okay, because this T depends on the embedding, but because you also have functors which can use a different embedding, you can show by universality that whatever you have is independent of the embedding. That's going to be one of the things. So that is why you need this universality, because you need to know that it's independent of the embedding. Okay. So you have this universality property, and this is what we wanted to construct. And what was the idea? So if we study varieties over field, so one of the things, this is a limitation of Nori's construction, that you have to only work with varieties defined over fields which are of characteristic 0. So there should be an embedding of the field inside C. Okay. This is a limitation. In particular, the question remains of, so characteristic key questions. You can say it's a question mark. Okay, now it says participants can see this key. Okay, so we can So then what is the directed graph? So now I've come to D. I think in the previous slides I forgot to change it from G to D. Directed graph D whose vertices are of the form x and x, y, n. Okay, so this is what I have later called D1. So we'll see that in order to get all the properties of this category of motives, we will refine D without changing the category. So the diagram, we will actually take a subgraph of D and it will be enough to give all varieties. That's the idea. So we have directed graph with vertices of this type, and the directed edges are of two types. So I think I mentioned this last time. X, y, n goes to x prime, y prime, n, where x to x prime is a morphism of varieties that takes y to y prime. And then we know that in that case, from hn xy to hn x prime, y prime, there is a map of homologies, singular homologies. And this is, and the other one is a boundary map where z is a subvariety of y, which is a subvariety of x. So, of course, though I have written it in this loose fashion, is a subvariety. It's a chosen subvariety. I mean, it's not that it is a subvariety and you think of any different embedding. The embedding is given. Okay, it's a subvariety in the sense that with a given embedding, right? Because, for example, you could take a line inside P2, and there are many ways in which a line can be, a P1 can be embedded in P2, but the embedding is fixed. Okay, so this is subvariety, and y is a subvariety of x, which means that the embedding is fixed. And given that fixed embedding, you have another arrow in your diagram, which is of this type, and this is the n can vary for various n. So for each, so a triple consists of x, y, and n. Okay, and n, of course, we know that because we are working with homology, n has to be greater than or equal to 0. Right? So we only have n greater than or equal to 0, which is relevant here. Of course, for this, n has to be greater than or equal to 1. No, this is just a diagram. There are vertices x, y, n, and between vertices I am giving you arrows. No, it's an actual it's an actual graph. And n is an integer. You want me to write this? Maybe I can write. And n greater than or equal to 0 is an integer. So we are choosing three things. Again, here where this is a subvariety means that it's a chosen embedding of y in x. Okay, it's not like subvariety which is the same way, same subvariety, same variety may be embedded as subvariety in many ways, but different ones will give me different pairs. So just as we do in homology each pair means you've got some topological space and a subspace, a fixed subspace. So Z is again is a fixed subspace that we are going to look at, and right? And singular homology then gives a map of diagram. This is the starting point. So singular homology using this embedding. Okay. So this particular embedding is relevant because we are going to associate to X the topological space of complex points of this variety. Okay. And that has a natural topology, which is the so-called strong topology, right, which is not the Zariski topology. And similarly for Y and Z, these are all topological spaces with the usual topology, okay, which is a locally compact space and so on. And again, the important thing is that it takes values in mod Z, right? So this is something specific about varieties, which requires some proof. Okay, so this is some classical theorem which is attributed to Lecture6 or somebody, that for varieties, the pair of varieties, the homology is finitely generated. This is because there is you can reduce it to calculations for projective space and where everything is finite dimensional. Okay, so something needs to be proved in order to say that these are finitely generated abelian groups. Okay. I mean, if I take a manifold, there is no reason why its homology is finitely generated. Okay, but for varieties of the topology, the homology is finitely generated abelian group. That requires some proof, and it's a true statement. So it gives a map of diagrams like this, and this is the map of diagrams that you want to complete into a morphism of into the category of motives. Okay, so this is the idea, and the idea is to use our construction here, right? This construction to construct for that particular diagram. I'm going to take R equal to Z, right? And I'm going to construct. Any question? Yes. No, this is not the R. I mean, here this notation is bad. This is D now, right? What is your question? There's a huge graph we constructed in the previous discussion, and that graph we have a map to D to mod Z, and I'm going to complete it into an abelian category by using this construction, this theorem. Right? That's the idea. Okay. Okay, so as I mentioned last time, the basic idea is to solve the problem for finite diagrams. Once you solve it for finite diagrams, then we'll see how we can put it together. So you have got a case of a finite diagram. So you've got a finite directed graph with a map of diagrams. What does this mean? This simply means I've got inside mod R, I've got a bunch of modules, okay, TV1, TV2, let's say TV3, and I've got some maps, right? PM1, PM1, PM2, PM3, and so on. Right? So I've got some such directed graph. It could happen that though V1 and V2 are distinct edges here, their images are the same and so on. We don't care. Okay. So that's a map of diagrams. Exactly like when we do category theory, we define products and co-products and so on. V1 and V2 TV1 may be actually isomorphic to TV2, in which case this may be an endomorphism, but we don't care. Okay. So we define, last time also we did this, so let me just, because it was somewhat badly written. So the idea is to look at endomorphisms of TV. As you vary over all the vertices, for each of them you look at the endomorphisms, and then you look at those endomorphisms which commute with the corresponding morphisms. Okay. So these are for each edge M, you have this morphism from the left. So LM, where have I done this? I've done it. Here VF is a collection of vertices in F, AF is a collection of edges or arrows, and for each edge M in AF, we take LM is the left vertex and RM is the right vertex. So for each M, TM is an element here. So TM is an element here. And then we are requiring that if I am looking at an endomorphisms of each vertex, such that if I apply first and gone somewhere. we have some sip of tea. This one. Okay, so and here you apply the other element ERM, and this is ELM. Okay. So I want to choose a tuple which consists of ERM, ELM such that if I go from here to here or from here to here, this diagram commutes. Okay. So have I done it in the correct order? No, I should have done it like this. I should write it somewhere separate. Erase. So I can go ELM, ELM. I can go by E of LM. And here I can take EM. And here also I am going to take EM. And here I am going to take ERM. And this is ERM. So I only want to look at pairs consisting of, let me concentrate on two vertices. Suppose there are only two vertices. I want ELM and ERM to be here if and only if this diagram commutes. Okay, so I only allow pairs of morphisms which commute with each TM. Okay. So that's what this says, because I'm going to take the kernel of DF. Okay. That means this minus this should be 0. Okay, so that requires that this diagram commutes. So it's a fancy way of saying that I'm going to look at all those endomorphisms I'm going to look at endomorphisms associated with each vertex, and only those endomorphisms such that for every edge, the corresponding diagrams commute. Okay. So I've reduced in some sense the endomorphisms. Of course, if you have an element of R, that is anyway going to work. Right? If all of them are a fixed element of R, that will work automatically, because all these M's, TM's are linear automatically. Okay. So of course, if EV is some fixed element A of R for all V, okay, that will work. But maybe more things will work. But as the idea is that as you increase the number of morphisms, the number of possibilities for this is reduced. Okay, so therefore that is reduced. Okay, and the category AFT for the finite diagram case is just the modules over EF and the functor. So finitely generated modules over EF. So first thing is note that since R is Noetherian and this is a finite sum, therefore this is a Noetherian R module, and therefore this is the algebra A, which is a Noetherian, is a finitely generated R module, and therefore it is also Noetherian. Okay, EF is Noetherian. So somewhere I should have remarked that. Maybe anyway. So this is finitely generated R module. And also, therefore, a functor from here to here, finitely generated EF module will automatically be a finitely generated R module, and therefore that will also be, there will be a functor like this. So they are natural forgetful functor of this kind. Okay, now I just remarked that which I said this. Now for each V, we have of course we have natural adduction of EF. EF is made up of various, is contained in the direct sum of endomorphisms of TV. So I can just restrict to that component, right, natural action of EF. And therefore, it's you can think of TV as an element of this. TV is, so in other words, so TV is an EF object. Oops. EF module. Sorry. Yeah, EF, forget the kernel notation. EF is just the module, is the collection of all endomorphisms of all the modules, such that for every M, the diagram commutes. Okay. So it's a collection of endomorphisms of each vertex. Okay, such that whenever I have two vertices and I take an arrow between them, which is any one of the arrows in the diagram, then this given endomorphism here and this given endomorphism here, I make a square out of it. That square is commuted. Okay, that's the state. So each of them is of course is a module, and the morphisms between them, which are given by the edges in F, are morphisms by construction, are morphisms of EF modules. Okay, so that is just a straightforward thing, and each M in F, this is a so you get a natural lift of the map P tilde from F to mod EF as required. There's nothing very serious here. It's just more or less this is by construction. Now, last time I got confused about this, I thought I would see it very clearly. So suppose you have two finite diagrams, and you have a commutative diagram like this. Okay? So this diagram is, in some sense, this is bigger than this diagram. Okay. But at this stage, even just a map of edges. So this is just an ordinary map of directed graphs. That's good enough. So that this is equal to this. Then you can just see that this diagram commutes, okay, where these vertical arrows are given by you. Okay, so these vertical arrows are given by you. So for every vertex of F1, I will get a vertex of F2, right? And I know that whatever that vertex goes to here is the same as what this vertex goes to, right? So if V is a vertex in F1, right? So something, then I have this P1V is nothing but, because of this, is P2 of U of V. So U of V is a vertex of F2. And here I would have taken P2 of endomorphisms of P2 of U of V. And these two are actually the same. Okay, P1 of V is the same as P1 of V is equal to P2 of U of V. So there's a natural map like this. For every, there may be more vertices here, that's okay. And similarly, there may be more morphisms here, but certainly the morphisms coming from here are giving edges here, are giving edges here. And so, and this diagram commutes, so that means that the image of the edge is going to be an image of the edge, and so again, the notion is exactly the same. So this diagram commutes. And since the diagram commutes, the kernel of that maps to the kernel of this. Okay, so there is a natural homomorphism of algebras. This. Yeah. Need not be, well, it need not be injective, of course, but the point is that under T1, then the two vertices will go to the same vertex. Which one? Doesn't matter. Yeah, but they will have to be the same because under T1 they are going to the same element. Okay. So I mean, I didn't even require that T1 is injective in some sense, right? So suppose two vertices, I mean, it's a good point, one should check these things. If you have two vertices V and W here, and suppose two vertices go to the same vertex here, okay, then check that the element of EF1, okay, take the element of EF1, each element of EF1 gives an endomorphism here and an endomorphism here, and these two are equal, then the endomorphism will be the same. Okay. So, I mean, some things have to be checked. Okay. I think in order to do this correctly, you have to expand AF to include identity, I think. You should always include identity maps on F1, just to avoid some nonsense. Okay, so one has to do it carefully. So always you add, maybe you not only take this but also take identity for all the morphisms and make it come. Okay. Right. So this gives a morphism of R algebras, EF1 to EF2, and once I have a morphism of R algebras, I will get a natural diagram of natural functors, forgetful functors. Right? From mod E1, EF1 to mod EF2, take a morphism, take a module over this, and you consider it as a module over this. Okay? So you will get a diagram, and then you can take the limit, direct limit construction, and you will get the category as the direct limit. Okay. Every object is the image of an object in mod EF for some. So what does it mean by limit in this sense? Every object is an object in the is an object in one of the finite stages. That's not a problem. But what is a morphism? That is more tricky. Yeah. Yeah. Or you're saying it should be in the other direction? I have to go wrong again. No, I done it wrong. Okay, let me just check. Again, in my slides, this has been a source of some confusion for me, clearly. I have said in my notes, I have said I've written direction. How did I get that? Let me see. Okay. So I didn't explain. Thank you. Oops. Okay. Yeah. So, yeah, maybe I should take some space in the next slide. Anyway, it will go. Okay. So I want to say actually you get a morphism like this. Let me write it once more and then explain. So I've done it wrong. Direct sum over V in F1. So I will just write without the V. direction O, N, E, F, P, L, N, E, R. And then the same thing for F2. Let me call it W just to avoid confusion. Let me call this N. Okay. Okay. So this diagram commutes, that is not a problem. The thing to understand, yeah. So the point is, why is the map actually from endomorphisms in the opposite direction? Okay. So the point is that this vertical component, when W is equal to U of V, right? This is actually the same component as that one. Okay. So we have more. So I can in some. So what am I saying? And similarly on this side. So if I take just the elements coming from here, if I project into the part which is only elements of this type, so maybe I should say, so if I now go to direct sum, so if I just take only those components, okay, I forget the components which are extra in F2, then and I project into that, then that is going to actually be in EF1. Okay, because if I go here and I go here, that is the same as going here, and that is 0. Right? Because I mean, maybe a picture, maybe a specific example will help. So suppose I look at two vertices, V and W, V and V prime, and then I add another vertex, V double prime. Now, whatever element I have here, it commutes with this as well as this. Therefore, if I take the projection only into these two parts, it is in the kernel here. Okay, this has, so maybe it's wrong of me to have said, written a diagram like this, maybe I should have taken the projection. That I have not checked, maybe that diagram also commutes. In any case, my point is, here is the diagram, and this is a bigger diagram. So this condition here on EF2 is more than the conditions on EF1. Therefore, if I project into the components corresponding to EF1, then I will get an element of EF1. Okay. So if I project into the components corresponding to U of a vertex, I will get an element of EF1. So I get a homomorphism of R algebras EF2 to EF1, and so thanks for pointing it out. Therefore, I get a morphism in this direction. Okay. By thinking of a F1 module as an F2 module. Yeah, so absolutely. So what are you asking for? Let's again, as you said, let's think of again a situation like this, that this part is F1, and then in addition I have added something, and this is F2. Okay, now what I am looking at is endomorphisms at each of these vertices, which commute with all the arrows in this diagram, then I am adding endomorphisms at these vertices, which not only commute with that diagram but also commute with all arrows which go in this direction or this direction. So if I now forget these endomorphisms and only look at the endomorphisms here, then of course it is commuting with the existing diagram there. So that's why I have an homomorphism of algebras like this. Okay, so thanks. Yeah, so it is in the opposite direction, and therefore there is a morphism like this. Okay, so yeah. Okay, so there is a functor like this, and now I can take the limit. So the next thing is to take the limit. Sometimes it stays, sometimes it doesn't stay. No, I have already written this. So it follows that we can form this as the direct limit of the category as f varies over finite subdiagrams, bigger and bigger subdiagrams. So yeah, so maybe your remark is relevant. We need f1 to be contained in f2. Okay, so maybe I should have said that f1 is a subdiagram of f2. In that case, it's correct. I haven't checked it in the other cases. So this is for f1 contained in f2. So it's a subgraph of. Okay, so what does it mean to say take the direct limit? So every object in the direct limit is, by definition, is an object in one of the finite stages. Okay, that's the definition of direct. Direct limit means you take all the objects at each stage, and so an object in the direct limit is an object at some finite stage. What is a morphism is much more tricky. Okay, because a morphism in each stage will give me a morphism in the next stage, okay, and which will give me a morphism in the next stage because there is a functor, but it should be a morphism at each level, right? So for every finite diagram, it should be a morphism. That means something here should give me a morphism at each level. That means when I go down, two morphisms may become different or may become equal. Okay, so because EF1 goes to EF2, right? So EF2, which one? Sorry, again, I got confused again. So you have what EF1 goes to EF2, right? So so morphisms are, as usual, are going to be slightly harder to understand, and the functor is the direct limit of the forgetful functors. So you just form the direct limit. Okay, so this is the construction, and I mean, so yeah, so this is as far as I wrote slides today. But now I wanted to explain. So can I go back to adding a page? I can just add a page, right? So this is roughly a summary of what, with correction, which I needed to do last time also, which I had made an error this time also, to say what is it that I did last time. Okay, so now the question is, how do I build this up into what I need? Okay, so as it stands, this constructs a category, but what we would like, according to Grothendieck, is not just that it's a category, but it should have all the properties of homology theory. Okay. Now, one of the standard properties, if you just look at Steenrod's axiom, Eilenberg-Steenrod axioms, long exact sequences will be long exact sequences because the functors are faithful exact. There is no problem about that. The main difficulty which you face is that you would like to have intersection. Otherwise, it's not of much interest. So, intersection pairing. So in order to do intersection pairing, one should be able to do tensor products. In order to do tensor products, the thing becomes more complicated because, if you take finitely generated abelian groups, there's no natural notion of tensor products. I mean, there is a natural notion of tensor products, but it's not very well behaved. Because tensor of two things can become 0 and so on, right? So, so what you would really like is to have what are known as good pairs. So these are or triples, if you like. Which are things of this type, where Hn of xy, the singular homology, is free. Okay, maybe free of rank 0, but free. So then we can talk about tensor products, right? I mean, the point is to talk about forming H. How do I form? Suppose I take x cross x prime. There is some dead part of the screen. Okay. So I would like to express this as a product, right? This is the Eilenberg-Zilbert thing. I should write to express this as a direct sum of HR xy cross tensor H n minus R x1, y, x1, y, and so on over R, right? So I would like to express this, but this formula is only true if is only correct if the things are free. Okay, otherwise you would get cancellations and so on. You get what is known as the non-exact sequence of tensors. So you won't get the product situation. But if these are well behaved of this type, then there is no problem for defining products. Okay. So that's one reason for taking it. And in fact, what one would ideally want is not to have this direct sum also. You would like to have only one such triple. So you want to look at pairs x, y such that not only is it free, it is 0 except for one n. Okay, so that anytime you try to write such a product, on this side there's only one term. Normally, what you get, if you look at if you try to define products in homology, you get what is called the Kunet spectral sequence. Okay, so ultimately you get a sequence of you get a gradation such that the associated graded is of this type. Okay. The problem is that I mean, if you have looked at homology, the problem is there is no natural way of taking an n simplex and writing it as a product of an r simplex and an n minus r simplex. There are various ways of doing it, and then you have to see that these various ways of doing it, they give the same element in homology. Okay, and so you would rather like to avoid that. Okay, so you would like to have a situation where this is true. So to get this good pairs is one of the more geometric parts of what Nori has to do. Okay, so it's as it stands, the category which has been constructed is the category of motives, but we would like it to have various properties. So what one would like to do is to show that instead of the original set of diagrams, I can restrict my attention to good diagrams, and good diagrams will give me the same category. I mean, good pairs. I should like to restrict the diagrams to those which correspond to x, y, n, which are good pairs, and for good pairs already I will get everything. Now how can you do that? That means every space should be possible to replace it somehow by a space which is made up only of good pairs. Okay, so that's the next task that we have in front of us. So how do I take a given pair xy and replace it by, or calculate its homology only using good pairs? So the idea is that if I can write x equal to x0 contains x1, contains x2, contains xn, contains y. Okay. Maybe xn is equal to y. Xn contains such that each of this xi minus 1, xn equal to y minus n. So xi comma xi plus 1. Suppose this is a good pair and it has only ith homology. It's an I good pair. Then you can calculate the homology by using this tuple, this filtration, because you can write your boundary maps. H, which way does it go? H, sorry, my numbering is wrong. Probably I should have started with n here, n minus 1, n minus 2, n 0. So the map should go from h0, and this is minus 1. So h0, x0, x minus 1 goes to h1, x1, x0 goes to h2. Sorry, I'm going in the wrong direction. No, I have done it correctly earlier. Sorry, because the maps go in. No, it's yeah, I've done it correctly earlier. Sorry. 0, 1, 2. So hn plus 1, hn, I'm getting something wrong. All I wanted to say is that you can write a certain complex by using the boundary maps. hn plus 1, this is correct. hn minus 1, 2, hn minus 1, hn minus 1, hn minus 2, and so on. And you'll get a complex of groups, and that complex of groups, one can see that it computes the homology. Right? Imagine the case where, let's forget that we are working with varieties. Suppose you are thinking in the case of a cell complex. So I can take 0 cell, 1 cell, 2 cell, 3 cell, 4 cell, 5 cell, and so on, n cells. And then at each stage, the relative homology is nothing but the number of attached cells. Okay, is exactly, so it's a good pair in the sense that hn relative to hn minus 1 is exactly n cells, is the number of n cells. It's a direct sum, right? And everything is going to be finite, so you can write direct sum over the number of n cells. Okay. And then there is a boundary map which goes to the n minus 1 cells and then goes to n minus 2 cells and so on. Okay. So you will get a complex like this, and that complex will actually compute the cohomology of the space. Now can we do such a cell decomposition, but now requiring that these are varieties? That's the question. Okay. So obviously you can't. You can't make a variety by attaching cells. But the thing is that, and first of all, the dimension would be wrong because you have an n-dimensional. If you have an n-dimensional variety, your cells would be of dimension 2n. Okay. So there are two problems. One is the dimension seems to be wrong, and the other is that, of course, cell attaching is not going to give you the right thing. But here is the first point. So, first step, replace x, y by x tilde, y tilde, which are affine. Okay. So, this is an old trick which goes back to Joan et al. Okay. And in fact, Grothendieck was very much aware of this trick and used it in order to talk about de Rham cohomology initially and so on. So what is the Joan et al. Trick? The Joan et al. Trick is take a quasi-projective, well, let's take first the case of the projective variety. So X is contained in Pn. And then you embed, you take, there is a natural bundle on Pn, which is, let us go, I don't know what notation to use, J of Pn, which is the sub of Pn cross Pn dual. So Pn dual, remember, is the collection of all hyperplanes that contain, which are hyperplanes in X. Okay. And this is the complement of the incidence locus. So here you can look at points P in Pn and a hyperplane such that P does not belong to H. Okay. So what is the fiber over a point here? A fiber over a point here consists of all hyperplanes which don't contain H. Okay. But every point in Pn defines a hyperplane in Pn dual. All the hyperplanes which contain it itself forms a hyperplane.
I think we should wrap up now. Yeah, somehow. I think the microphone is this way. We need to wrap up actually, we are running out of time. Yeah, so we'll continue from here next time, and the session ends today here. Thank you for being here. Have a good day.